Hello everyone. Let me ask you a simple question. Have you ever seen water droplets forming on the lid of a boiling pan? That's liquid water turning into vapor and then back into liquid. Here, two phases, liquid and gas, exist together in balance. This is a perfect example of a heterogeneous equilibrium because the phases involved are different. Another case is when solid calcium hydroxide dissolves partially in water to give calcium ions and hydroxide ions. Written as CaOH taken twice, solid gives Ca2 plus aqueous plus 2OH minus aqueous. In heterogeneous equilibria, solids, liquids, and gases can all coexist, but the equilibrium involves only the phases that vary.
Now, how do we write the equilibrium constant for such systems? Here's the key point. Pure solids and pure liquids have constant molar concentration, so we do not include them in equilibrium expressions. For example, take the decomposition of calcium carbonate. CaCO₃ solid gives KO solid plus CO2 gas. In this case, Kc equals concentration of CO2 and Kp equals partial pressure of CO2. Notice that calcium carbonate solid and calcium oxide solid do not appear in the expression. They are constants. This is why in heterogeneous equilibria, only the gaseous or aqueous components appear in K expressions. Let's look at this process in detail. When calcium carbonate solid decomposes to calcium oxide solid and carbon dioxide gas at 1100 Kelvin, the equilibrium pressure of carbon dioxide is measured as 2.0 times 10 to the power 5 pascals. Converting this, the equilibrium constant Kp equals PCO2, which is 2.0. So here, just by measuring the gas pressure, we can directly calculate the equilibrium constant. This shows how simple heterogeneous equilibria can be when only one gaseous component is involved. Another interesting aspect is the units of equilibrium constants. They depend on the stoichiometry of the reaction. For example, for hydrogen gas plus iodine gas giving 2 hydrogen iodide gas, written as H2 gas plus I2 gas gives 2HI gas. The constant has no units because the mole ratios balance out. But for nitrogen dioxide dimerizing into dinitrogen tetroxide, written as 2NO2 gas giving N2O4 gas, the equilibrium constant has units, like mole per liter or bar. To make things consistent, chemists often define equilibrium constants in dimensionless form by dividing concentrations or pressures by standard states. But in normal calculations, always check if your K has units. Let's solve a numerical example to understand better. Consider the reaction carbon dioxide gas plus solid carbon gives 2 carbon monoxide gas. Here, Kp is 3 at 1000 Kelvin. Initially, PCO2 is 0.48 bar and PCO is 0. At equilibrium, let the decrease in pressure of CO2 be x. That means PCO2 becomes 0.48 minus x and PCO becomes 2x. Substituting in the expression Kp equals PCO squared divided by PCO2, we get 4x squared equals 3, multiplied by open bracket 0.48 minus x close bracket. Solving this quadratic equation, x comes out to be 0.33. Finally, equilibrium pressures are PCO equals 0.66 bar and PCO2 equals 0.15 bar. This shows how algebraic substitution is used in heterogeneous equilibrium problems. Now let's talk about why heterogeneous equilibria are important. They govern thermal decomposition reactions like the breakdown of calcium carbonate into quicklime and carbon dioxide, which is used in cement manufacturing. In metallurgy, the purification of nickel involves the reaction nickel solid plus 4 carbon monoxide gas gives nickel carbonyl gas. Another example is silver oxide reacting with nitric acid, forming silver nitrate solution and water. These processes involve different phases and show why heterogeneous equilibria are central to industrial chemistry. From steel production to fertilizer manufacturing, these equilibria dictate efficiency and product yield. To summarize, heterogeneous equilibria occur when substances in different phases exist together at equilibrium. Pure solids and pure liquids are excluded from equilibrium expressions because their concentrations are constant. Only gases and aqueous ions are considered in Kc and Kp. The units of equilibrium constants depend on the stoichiometry of the reaction. And finally, these equilibria are essential for processes like decomposition, metallurgy, and salt-acid reactions. So next time you see chalk decomposing on heating or vapor above a liquid, remember, you are watching heterogeneous equilibrium in action. So, to wrap up, heterogeneous equilibria teach us how reactions involving multiple phases reach balance. From classroom examples like calcium carbonate decomposition to massive industries producing lime, steel, and nickel, these principles are everywhere. I hope this session helped you understand why equilibrium constants for such systems are written differently and why solids and liquids are excluded. Keep observing chemistry around you. Equilibrium is happening more often than you realize. See you in the next session for more fascinating insights.